So if you didn't have second semester general chemistry, this might be relevant. We looked, and since I screwed up the oxidation state one, we have looked at equilibria, right? What an equilibrium reaction is. Yeah? Probably.
Yeah,
okay, then let's...
First unit?
Yeah, that's what I would have thought, but I also thought oxidation reduction was done in the first unit, and I was wrong about that. So, in an equilibrium reaction, we have reactants that go to products, and we're saying in an equilibrium that those products can go back to reactants. So it's the balance between reactants and products, right? We can refer to that balance by the equilibrium constant, capital K, which is always calculated as the concentration of products divided by the concentration of our reactants. Right? We also had, because I always forget the equation, we mentioned our Gibbs free energy, so it's up there in really tiny letters. The Gibbs free energy change for any reaction is the Gibbs free, or the standard free energy, plus the non-standard section. Okay. Q is effectively K. Pretty much the same thing, sort of. Q is what K, or is how K would be calculated if I was not at equilibrium. Okay, that's what Q is. So it's just saying I'm not at equilibrium, that's it. Okay? What does this all kind of mean for us? Well, let's take a look at the meaning of an equilibrium constant. What does it mean if my K is really, really big? If it's a number much greater than 1, the concentration of products must be massive, the concentration of reactants must be tiny. Why must the reactants be tiny if the products are massive? Can't I have a large amount of reactants and a large amount of products? Why not? Where did the products come from? The reactants. Okay. Where did the reactants come from in an equilibrium reaction? The products. So we have a set amount of material. Some of it can be reactants, some of it can be products. I can't have large amounts of both because, well, where did I get those large amounts from? Okay, I can have equal amounts, but not large amounts, necessarily. So if I have a really large K, okay, and we'll talk about the meaning of that one here in a second, that's saying the products are favored. So if I go back and look at that reaction A goes to B, I would expect a large concentration of B to be present. Okay. What if I had a very tiny K? Okay, and very tiny means much smaller than 1. Notice I'm not saying negative, and we'll get again to that statement. What does it mean if I have a very small value? The reactants are favored. And what does it mean if K equals 1? Say that again, Jen?
Wouldn't the reaction and the products be similar?
The product and reactant concentrations are equal to each other. Okay. That's about it. We don't really get anything useful out of that beyond that. We don't have a favoring one way or another. We're just saying that we get equal concentrations of both. Okay. If we have a K equal to 1, it's not particularly useful information. The useful information comes in when we have Ks that are either really large or really small, okay? Because those push the extremes of our reactions. How does that tie back to energy? So if we looked at an energy diagram, and I had a reactant, and I had products that were lower in energy, would I expect this reaction to favor the reactants or the products? Why the products? They're more stable, they're lower in energy. So we would expect in this case to have what value for our K?
Positive, or greater than 1.
Greater than 1. Okay? What is another characteristic of this energy diagram? So we know we have a K that is much greater than 1. What else do we know about it? And I think you were starting to say it. It is exothermic. If it is exothermic, we can say that our delta H is negative, right? Less than 0. Right? The delta H we said isn't the greatest thing to be looking at. We should probably be looking at our delta G. The delta G in this case would then be, whoops, so I gave away the answer.
Negative.
Also negative, less than 0. So by applying our information about K, and we can compare that back to our delta G. If we get K values that are very, very large, we're getting very, very negative delta Gs, typically. Right? So there's a distinct relationship between them. What does it mean if we have a large K? Well, that means we have lots of products. The reaction favors the formation of our products. Same idea happens, but in the reverse. If we had a very small K, what is that going to mean about our delta G? Our delta G should be positive, greater than 0, which means what type of reaction? Endothermic. Right? What does that mean about the reactants or products being favored? The reactants are favored. Right? So it's trying to interpret all of that information. So when we talked about at the beginning that thermodynamics existed in this space, the distance between our reactant and product energy, that's what we're talking about. We can quantify all of that information. We can also just kind of relate and make sure we've got some approximations that allow us to interpret those relatively quickly. Kind of make sense? Okay. Because I screwed up on the oxidation state, I decided I should probably double back and make sure that we're all on board with the basic rules applied to redox. So, oxidation state. Okay? There are rules that are associated with oxidation state. First and foremost, which isn't on there, our oxidation states are things that you must solve for. Okay? They're never given to you, well, they're very rarely given to you explicitly. Because when we look at structures, we're typically specifying the formal charge. And the formal charge, while related to oxidation state, is not the same thing. Okay? So when determining our oxidation state, there's a couple rules that come out of it. Number one, we need to know the charges from any ionic compound, okay, which might sound a bit weird, but you guys probably know this. If I gave you sodium chloride, what is the charge on sodium? +1. The charge on chloride? -1. So you've probably already memorized the ionic charges. We need to do that because if I want to determine the oxidation state, I have to be able to solve for the balance of protons and electrons on each atom. Well, if I look at the rest of the rules, I don't know the oxidation state for either sodium or chloride. How would I ever figure it out? Well, because it's an ionic compound, what I'm looking at is sodium ion and chloride ion. I now know the charges on those as independent units. I can then determine their oxidation states. Okay? Yes, it's trivial, but that's how we'd be doing it. Kind of, sort of? Okay, we'll come back to that in a second. Rule number 2, oxygen will always have a -2 oxidation state. Is that always true? No. There are 2 exceptions. And we'll look at those exceptions. O2, H2O2. What is the oxidation state of oxygen in O2? Ends up being 0. What is the oxidation state of oxygen in H2O2? Becomes -1. Okay. That's because oxygen is doing obnoxious stuff in H2O2. Okay. The reason why oxygen always carries a -2 oxidation state has to do with the balance, again, of protons and electrons. What is a characteristic of oxygen? True. Keep going. Of particular concern would be its balance of protons and electrons. Could we change the protons? No. Could we potentially change the electrons? Yes. Why, when we look at oxygen, does it always gain 2 electrons? Lots of atoms make octets, so I don't quite accept that. What was yours?
It's got 6 inside our shell. It's easier to gain 2 than to give up 6.
Sulfur would gain 2, but sulfur isn't always a -2 oxidation state. So I don't accept the octet. What did I hear over here? I think Terry and Jen both said something. What did you say? And the valence electrons goes back to what they're suggesting with the octet. Electronegativity. What is oxygen's electronegativity? It's really high. How high is it? It's the second most electronegative element on the periodic table. The only element that would ever take electrons from oxygen would be fluorine. We don't make OF bonds. Okay. So because of that, what ends up happening? Well, oxygen will always carry a -2 oxidation state. Where would there be an exception? Bonding to fluorine, it would potentially lose electrons. What if it bonds to itself? It's now sharing equally those electrons. Because of that sharing equally, that messes with the oxidation state. That's why we see exceptions. Okay? The oxidation state is coming from what it's bonding to, which is a difference in electronegativity. Oxygen, being the second most electronegative element, almost always carries a -2 charge. It is very rare to find exceptions because there's only 2 elements that could possibly change it on the entire periodic table. No other element do you memorize because, well, there's always going to be an element either above or below it that could mess with that oxidation state charge assignment. Okay? And we look at the 2 exceptions. O2, what is oxygen bound to? Itself. There's an exception. H2O2, what is oxygen bound to? Itself again. There's an exception. Okay. What is happening exactly within those exceptions we don't need to worry about. Just realize there are kind of exceptions there. Okay. When we get into how we determine the oxidation state or number, the sum of the oxidation states for every single element in an individual unit, okay, will always be specified in the upper right-hand corner. Okay, so the sum of all of those oxidation states, yes, is written in the upper right-hand corner. But it's kind of tedious to call the sum of the oxidation numbers in the right-hand corner. So what do we call it instead? The charge. So you're always told the charge, and the charge is the sum of the oxidation numbers. Okay? Where it becomes tricky is we then say, well, that's the unit. Well, what is a unit? It can be a molecule, it can be a compound, it can be an atom. Any one of those things are valid. And this is why people tend to get oxidation state and charge confused, because there are several cases where the oxidation state equals the charge. Like if there's only one atom, the charge is the oxidation state. We start to say, well, what's the difference then? There isn't a difference. Well, there is a difference. The charge applies to a unit, a larger structure than just one atom. The oxidation state only applies to an atom. Okay? So we've got that formula written out there that could theoretically help us out with that. If we went back to our sodium chloride, This is why we needed rule number 1. Because we take the number of the element, well, there's 1 sodium times the oxidation state. Well, being the jerk that I am, I said you couldn't memorize that. You had to solve for it. So it's an unknown variable. Plus the number of chlorides, well, there's 1 of them, times its oxidation state. And again, I don't know what it is. That, when added up, must equal 0. This says x plus y equals 0. How many possible solutions are there to that? There's a lot. There's an infinite amount of solutions. Okay? It might be nice if we had only 1 solution because we're looking at an oxidation state. Okay? So how do we then solve that equation with 2 variables? That's where rule 1 comes in handy. Because it's an ionic compound, the unit that I'm looking at is not sodium chloride, but I can split that into the ions, sodium ion and chloride ion. So now when I go through and solve, the unit is sodium ion. How many sodiums are there in sodium ion? 1. The oxidation state you must always solve for. There's no other elements present, so that then must equal the overall charge. The overall charge specified in the upper right-hand corner is +1. I know the oxidation state is +1. So people tend to confuse charge and oxidation state because of that. But they are 2 distinctly different things. Right? The unit can be an atom, it can be a molecule, it can be a compound. Okay? But that is our charge. The oxidation state is only the atom. Yes?
So will you give us Na plus, or?
So because of rule number 1, you should be able to recognize that Na, sodium chloride, is an ionic compound. How do we know that's an ionic compound?
Metal on that.
It's a metal and a nonmetal. So way back when we talked about unit number 1, we looked at what are the different types of bonds, ionic, polar covalent, and nonpolar covalent. We had rules for identifying those. You needed to know those rules. So you need to know that to be able to recognize that that compound is ionic. We can split that into the ions. Okay? So I would not tell you Na+, I would tell you sodium chloride. And you'd have to tell me the oxidation state for sodium.
So, but like, would you want us to show that, can you just know that it's plus and minus, or do you have to show that you're actually?
So that's going to come down to what kind of work would I ask you to show for this kind of question. I am hard-pressed to put this as a show your work kind of question, because a lot of the mathematics that are done in this calculation are things that can be swiftly done in your head. Well, if it's something that can be swiftly done in your head, I don't want you to write it down, because most people skip over that, and then somebody that knows what they're doing then loses points. So it's not a show your work type question, it would be more of a multiple choice. So if we looked at some more examples, charge, oxidation state, the charge is shown up top and that little orange circle. So for the very first one, copper metal, what is the charge on that molecule or that unit? It's 0, there's nothing written there. When I move to the nitrate, what is the charge on that one? -1, because it's again written in that upper right-hand corner. What happens when I move to the last copper? I now know the charge on that one is a +2. It is different from the first copper. Kind of comes back to examples of sodium. What is the difference between sodium as a metal and sodium ion? The charge. You might say, well, but it's still sodium. Right? You ingest sodium metal, you are probably dead rather explosively. You ingest sodium ion, you've got a lot to ingest before you die, because we need sodium ion to function. You end up dying because you've ingested so much sodium ion that you've create an imbalance in your muscles, and your muscles can no longer function properly. And I'm like, well, that's not a big deal, right? I don't need my arm to move, but I do need blood to move through my body, and the blood moves through the body using your heart, which is a muscle. If the muscle doesn't have the proper balance of ions, you kind of die. Okay? Kind of makes sense? A lot of you are med people. I did that interpretation right with the sodium ion, right? Okay, just checking. I think they use fancier words than I did, but I'm pretty sure that's what's going on. So what happens with oxidation state then? Right? Well, in that very first one, I said you have to solve for it. The sum of the oxidation states equal your charge. Well, how many atoms are there? 1. Times the oxidation state. I don't know what it is for copper. I have to solve for it. There's no other atoms present, so then this must equal the overall charge. The overall charge, given in the upper right-hand corner, was 0, and I can now say the oxidation state for copper metal was 0. The charge for copper metal also happened to be 0. But that's not quite purely a coincidence, but it's a kind of a coincidental observation. It's a different thing. Kind of make sense? So let's see how well you've been tested on this. Let's jump to the tail end here. Let's take a look at sulfate. What is the oxidation state for sulfate?
+6 for sulfur, -2 for oxygen.
What was the question again? I asked for the oxidation state, which applies to individual atom. But I asked for the oxidation state of sulfate. Is sulfate an individual atom? No. So it was a jerk off of a question because you can't possibly answer that because they don't make sense. The oxidation state only applies to the atom. The charge, which is what Anna suggested, on sulfate is -2. But that's the charge, not the oxidation state. What Ray went through and did was solved for the oxidation state for each of the individual elements, right? Which would be a better question. So what is the oxidation state for the oxygen in sulfate? -2. Why was that said so fast without doing any calculations? Rule number 2 in our list of oxidation states was oxygen always has a -2 oxidation state, right? To go through and solve for the sulfur, well, there's 1 sulfur. I don't know its oxidation state, plus how many oxygens? 4 times the oxidation state being -2. This then must equal the overall charge, -2. We can go through and then solve x minus 8 equals -2, x equals +6. Make sense? So that's our old school way of determining oxidation states according to general chemistry. That was, in theory, done in our 130 classes, though I've talked with some colleagues that said they've had to skip it, for instance, this semester, so it may not have been discussed in detail in your 130 class. In 152, they absolutely should have gone into gory detail about oxidation states because it is a requirement for 152. Right? What we would then do is apply this out to our reactions. Certain reactions look at a transfer of electrons. So if we look at the reaction that we're starting with up there, we'd go through and determine the oxidation state like we just did in that previous slide, which, by the way, was a new slide, sorry. What was I talking about? Oxidation state for each of the elements. I'd go through and look at every element that shows up on every side of each side of the equation and determine its oxidation state. So I've got iodine in the reactant, I got iodine in the product. I determine the oxidation state on both sides. Oxygen, both sides. Carbon, both sides. Right. One thing that you will likely notice is if an element shows up in multiple spaces on one side of the equation, the oxidation state is very commonly the same in both those cases. Typically the one that shows up is oxygen. And well, oxygen is always a -2, so we didn't have to worry about that unless it's all by itself. Okay? When we then go through to look at our oxidation states, we can see that they changed. Well, the only way our oxidation states change is by transferring electrons. So in the case of the iodine, it had to gain electrons, okay? Which a lot of people get kind of freaked out at, because I started at a +5 and I went to a 0. My number got smaller, and yet somehow I gained something. That means I'm adding. Why would the number get smaller? I'm adding electrons, and electrons happen to be -1 charge. So by adding a negative, I will get smaller. Right? With no change, we won't worry about that one. The next one, carbon went from a +2 to a +4. The number got bigger, and yet I'm lost. I have a negative. How does the number get bigger if I'm losing? Same process, I'm losing a negative. A negative and a negative is a positive. Right? So recognizing how those numbers kind of swap out on you. Kind of makes sense? Because it's a bit tedious to refer to each element as gaining electrons or losing electrons, that's where we invent the new terms oxidation and reduction. That was the Leo says Gur or the oil rig. Okay. Whoops, come back here. I don't really care which one you use to memorize it, though Leo says Gur is by far superior, and anybody that tells you different is wrong. Okay. One more little bit of trivia. We've got oxidation and reduction. Right? The whole gain of electrons and loss of electrons is actually kind of an artifact. That's a recent discovery. We didn't even know we had electrons until about 1900. Oxidation and reduction are old terms. Those are terms that are coming probably not BC, but darn close, okay, to 0 AD. Okay? So why did we use oxidation and reduction and not looking at the transfer of electrons? Well, we didn't even know we had electrons, so we had to come up with some other explanation for what's going on. Oxidation, I would argue, is the biggest one, or why that name came first. Okay? We went through several kind of ages or epochs, through advancement in technology, right? We had the Stone Age, and we had the Bronze Age, we had the Iron Age, thank you. What is special about the Iron Age? And I bet iron came before bronze. What is the issue with iron? Oh, we're out in battle, we're fighting with our iron swords, but it got all wet and rainy. The iron rusts. Okay. It rusts when exposed to oxygen. So what are we observing? We're observing the oxidation of the material because it's been exposed to this oxygen molecule. That's where our oxidation term is coming from. We've increased oxygen. So we can look at a reaction, okay, anything that was oxidized. Take a look at the carbon. That was the one that lost electrons. On the reactant side, it had how many oxygens? Reactant side, bound to the carbon. 1 oxygen bound to the carbon. On the product side, 2. What happened to it? It was oxidized because we increased the bonds to oxygen, which is what Jen was suggesting. Again, this was back in my, I thought we'd already talked about this stage, so I apologize for that. Okay. What happened to the other species? Well, that's our reduction. That term is a little bit harder to nail down, but we could do it based off of oxygen again. What species was reduced? Well, that was our iodine. What happened to the iodine in the course of the reaction? We went from I2O5, so 5 oxygens bound to it, to what? I2. What happened to the amount of oxygen bonds? Also known as reduced. We reduced the amount of oxygen bonds. There's our reduction term. If we bring in our electrons, what happened to iodine's oxidation state? Went from a +5 to a 0. It was reduced. The number was reduced. Right? So we can tie back kind of the definitions of where those terms came from and how that relates to our reactions. Not all reactions involve oxygen bonds. Conveniently, in biochemistry, nearly all redox reactions that we're going to be concerned about involve oxygen bonds. Okay? So that makes it a little bit easier to manipulate. Advance. Oh no. So, we got oxidation and reduction. One more thing we need to make sure we review from general chemistry is we also have this term of oxidizing agent and reducing agent, which we conveniently already kind of talked about when we talked about, begins with a C. C-A-R-B-O, carbohydrates. With our carbohydrates, we had the reducing sugars. That whole reducing, what did we say was happening? What happened to the sugar if it was a reducing sugar? It was oxidized. We increased the oxygen bonds. If we have a reducing agent, aka the reductant, the molecule donated electrons to another compound and was thereby oxidized. We increased the bonds to oxygen on our reducing sugar. It was oxidized. Okay, so our ing or agents or ANT appended to our oxid or reduce becomes problematic because we're now referring to the opposite thing to the molecule we're looking at. They're causing something else to do that action. So a reducing sugar is causing something else to be reduced, which means it necessarily had to be oxidized. Make sense? Yeah, it's confusing. So anytime you see oxidizing agent or reducing agent, what you're being asked about is the opposite thing. So instead of seeing oxidizing agent and going, okay, now I got to think about what this means, be like, okay, well, the oxidizing agent was the one that was reduced. Reduced meant gain of electrons. Now I can go back to my equation and I can go through and determine oxidation states and identify the one species or the one atom that gained electrons. Because it gained electrons, that means it was reduced, which then means it was the oxidizing agent. Anytime I see a question that involves the ing or the ants, I write exactly what's written up there. Okay? Because it is very easy to lose track. You end up doing opposites all the way through. So if you can actually write it down, you don't have to think about it. Your answer is already put down. It's now just a question of answering the easiest part of that question. Does that make sense? Why does that not make sense, Mark? Or are you just like, that's stupid, why did we do this?
More, yeah, that.
What's that?
I'll get you after class.
Okay.
Rather than
Okay. That's fine. It's not wasting. Which then kind of kicks us up into the organic level. Remember, biochemistry is, and I added some extra words on this one, merely an advanced simplified organic chemistry class. Okay? We're going to be primarily concerned about the states of carbon, not, say, the states of iodine or other species. Okay? So because carbon is the one changing its oxidation state, if we're aware of the oxidation, primary possible states of oxygen or carbon, we can then go through and kind of simplify our rule set. And this was the rule set that Jen was kind of suggesting for our process. If we look at an atom, if we increase the oxygen, then we've increased our oxidation, thereby we did an oxidation reaction. What if we decrease the oxygen? We did a reduction. So we can look at our structure and skip determining any of the oxidation states or transfers of electrons or any of that, and just said, well, there's more oxygen. Well, if there's more oxygen, it was oxidized. and we can simplify our process through. Okay? The common oxidation states that you'll find, we can take a fully saturated carbon. So I would actually add hydrogens out there. CH4. If I add one oxygen bond, I end up with an oxidation reaction. An oxidation reaction to what functional group?
Alcohol.
If I oxidize it one further, what do I have?
Ketones.
I would argue you have a carbonyl. We haven't specified where that carbonyl is located. It could be in the chain, which would be a ketone, or it could be at the end of the chain, in which case it would be an aldehyde. Okay. We've seen both, and in fact in our carbohydrate chapter we focus primarily on aldehydes. If we oxidize it again, what do we have?
Carboxylic acid.
Now we have a carboxylic acid. This one by definition has to be at the end of the chain. If we oxidize it again, we have a what? It's not an alkene. That's carbon bound to oxygen. So there was one sheet saying CO2. Well, it already said C and 2 oxygen, so you are simplifying it a little bit. I would go with Mark, even though it's still kind of a bit silly naming it. It's carbon dioxide. Carbon dioxide is our ultimate oxidation state. We can't oxidize any further than that. Okay? We could go through and determine the oxidation states. The rules that we just looked through for Gen Chem don't work very well because when we're looking at an organic molecule, we have a lot of individual pieces attached. And in that formula system that we use for the general chemistry model, we are assuming that every atom in that compound has the exact same oxidation state. In a larger molecule, say in biochem, that's not true anymore. You will have carbons of varying oxidation states. So we could be asked to theoretically determine the oxidation state in a more simplified fashion. We can't do it the way Gen Chem does it. That's where we run into this next thing, homolytic minus heterolytic. Okay? Which is really going to be your valence electrons minus the electrons distributed based on electronegativity. What the hell does that mean, Mike? That's way too many words. Okay, so let's look at it. Let's look at the oxidation state for that alkane, the carbon. Well, how many valence electrons does carbon have? 4. If we were to look at the bonds, okay, we've only got one shown, or there's 2 shown here, but let's take a look at the electrons in that bond. There's 2 electrons there. Where are those electrons going to spend most of their time? With the more electronegative element, which Mark you're suggesting is carbon. Does everybody agree with that? It's a tricky one. Yes, carbon is more electronegative than hydrogen. It is by definition a nonpolar covalent bond, but that's because the difference in electronegativity is so small. There is still a difference in electronegativity. Mark is right. Which means the electrons in that bond spend most of their time with the carbon. Because we're looking at the distribution based on electronegativity, I'm going to say carbon owns those 2 electrons. What does it do with the 2 electrons bound to the other hydrogen? It's going to own those. So it owns all 8 electrons. What happens to its oxidation state? It'll be 4 minus 8. I get minus 4. Let's go through with the next one. And again, I'm going to simplify it at first to put hydrogens in. Let's determine the oxidation state of our carbon. Again, I'll just make it the red one. How many valence electrons does carbon come in with? It always comes in with 4. Doesn't change. Minus the electrons it owns. Okay, well, how many of those electrons does it own? It only owns 6. It owns the electrons bound out to the hydrogen. Why does it not own those purple electrons to the oxygen? Oxygen's more electronegative. So I end up doing my calculation, and I get 4 minus 6. The oxidation state is -2. Going from a -4 to a -2, what happened? It lost electrons. That's why it became more positive. By losing electrons, it was an oxidation reaction. Look at what happened to the number of bonds to oxygen. Oh, they increased. So our formula makes sense for how we calculate this out. Kind of makes sense? Okay. Let's throw in one last wrinkle on this, which I'll do on that alcohol structure. So I'll erase these now. Instead of those being hydrogens, I'm going to make them carbons. I now want to know the oxidation state on that carbon. So still 4 valence minus. Whoa, that was the wrong eraser. Does it own the purple electrons? No. Does it own the blue electrons? Yes. So I'm just going to write that in for the moment. -2. Okay, and then we said green, potentially minus something. Does it own those green electrons? Why did you say some of them? And I think I heard you say shared.
Because it's the same electronegativity, so it only gets one.
They have the exact same electronegativity, which means the electrons in that bond split evenly. Which means our center carbon is only getting one of them. Which means I will subtract 1 here. What happens on the other side? Same deal. I can only subtract 1. What happens? I end up with a 0 oxidation state. Kind of makes sense? Notice the oxidation state for this alcohol, technically, what is that, isopropanol, is slightly higher than if it was methanol. Why is that the case? The oxidation state for the structure we have shown for that carbon was 0. The oxidation state for the one that is now erased, where those were all hydrogens, was -2. It's still just 1 oxygen. Why is the oxidation state higher? Has to do with the hydrogens versus the carbon. When we compare those two structures, carbon is more electronegative than hydrogen, meaning I have more electronegative bonds to that center carbon, which means its oxidation state is higher. Okay? So I want you to be able to determine your oxidation states in the general chemistry method and the official oxidation state anywhere in a molecule, and kind of superficially looking at it, did it oxidize, did it reduce?
So this is, I know last semester, okay, we had this discussion where it's for the easiest method, instead of increasing the bonds to oxygen, you said increase the bonds to a more electronegative.
It's the levels of questions that we're looking at. So let's run through it again on the level of question that can be asked. Number 1, what is the oxidation state on something other than carbon? So that's following our general chemistry method. You're given a formula. In the case of a formula, you really have to go back to the general chemistry method and assume all elements of the same type in that compound have the same oxidation state. You can determine your oxidation state. Okay? Method number 2, I give you a structure, point to an atom and say, tell me the oxidation number. we have to do this. Do what's on this slide, yeah. The homolytic versus minus heterolytic, or valence minus the distribution based on electronegativity. Okay? So those are both calculations. The next part of this is that when we look at a now reaction, I want to be able to decide, was that oxidation or was that reduction? Multiple ways to decide that. One, determining the oxidation state of all of the elements on both sides of the equation and see, did they change? Right? And then how did they change, and tie that back to reduction or oxidation. Okay, bless you. The other way is to go through and say, well, what happened to the amount of oxygen bonds? Did the oxygen bonds increase? That's oxidation. Did they decrease? That's reduction. What if the amount of oxygen bonds does not change? They're equal, so is it reduction or is it oxidation? Neither. Didn't happen. Nothing happened. Okay? Or no reduction or oxidation happened. Okay? We can also kind of potentially expand that out to saying electronegativity. When we're looking at oxidation, we're increasing the bonds to electronegative atoms. Technically more electronegative than the previous atoms. Okay? That is a much more advanced question. I won't ask that. I'm more concerned on, do we see oxygen increasing? Make sense? Or decreasing? That was a lot of time. So we're going to move on. So we're now going to look at some kind of important molecules involved in energy. First big important one, nicotinamide adenine dinucleotide, also known as NAD. Okay? More appropriately specified as NAD+. Okay? NAD+ will react to become NADH. Balance that equation. What would I need to add to it? So we just compare both sides of the equation. Don't get lost in the structure stuff down there. That's nonsense. Just deal with this. Okay, we need a hydrogen, right? There's an H on the right. There's not an H on the left. So let's put in an H. What charge should that H be? Okay. I heard a couple things, positive and negative. If it's positive, is my equation balanced? No. Then the result would be a positive, and this structure should better be written as NADH plus 2. It's not. It's written as NADH, which means there's no charge, which means the hydrogen is actually negatively charged, also known as a hydride. Thinking back to our organic chemistry, how stable is hydride? Not at all. Okay. So if we're looking at biological systems, the transfer of a hydride seems really, really sketchy. Okay. Which is why biochemists say, well, I'm not transferring a hydride, I'm transferring hydrogen ion. But then we run into that issue that we just addressed. Charge doesn't balance. What does NAD plus deal with? What is it? An oxidizing agent, which means it caused something else to lose electrons. So what does that mean? NAD plus what must happen to NAD plus?
Reduced.
It was reduced, thereby it must accept electrons. And that is very typically how your reaction gets written. Okay? We should have all sorts of problems with this. Okay? We said hydride shouldn't get written because it's highly unstable. What the hell do you think an electron is? Even worse, the reason why hydride isn't stable is because hydrogen isn't very electronegative, so it can't stabilize the electron. Okay? Not only that, but hydrogen is so small that the electron doesn't have a lot of space to move. What's the electronegativity of an electron? There isn't one because it's a free electron. So it has no electronegativity to stabilize the charge. Okay, so that's taking me the opposite direction of where I want to be, more stable. Okay, and where does that electron now exist? In a point charge. At least when it was associated with the hydrogen, it had an orbital in which it could move. We don't even have that. So why are they writing it out in this fashion? They're trying to show is the transfer of electrons because we're running redox reactions. So depending on our point of view within how we're looking at our redox reactions, we may write it as H minus, we may write it out as H plus and an electron. Okay? I personally think it is dumb to show it as an electron. That is how the standard notation though. So when you look up an equation, you are very likely seeing it written as E minus plus H plus NAD plus to NADH. Okay? That's just the standard format. That's what it is. Okay? Is there a question back there, guys?
No, she's laughing at my notes.
Would you need 2 electrons for this equation?
Oops. You tell me. What is the charge on the right-hand side of the equation? Overall charge out here.
0.
What is the overall charge on this side of the equation? There's a +1, there's a +1, and there's a -1. I know that looks horrible. Those cancel, I'd have +1, which means did I balance it? No. What else do I need? I need a second electron. So not only do I have one electron that's incredibly unstable, chilling on its own, I now have 2 electrons. Yeah, I completely disagree on a fundamental level for that notation. But again, that is the accepted notation. It makes a hell of a lot more sense to call it H minus. And we look at our chemical reactions, guess what's being moved? H freaking minus. Okay, so let's clean that up. Now make it more difficult, because we love that, right? This structure here, big old nasty thing, is our NAD+. Okay, we have the nicotinamide in red. We have, make sure oh gosh, this one's confusing. The nicotinamide, and then they say adenine. Adenine is here in blue. And this is particularly irritating. Then they say dinucleotide. Dinucleotide means 2 nucleotides. What's in purple is another nucleotide. That nucleotide happens to contain nicotinamide. Right? So they're saying there's piece 1, piece 2. If I put those pieces together, that's now dinucleotide. It's a bit redundant. It's like saying it's 1, 3, 4. That makes sense? 1 plus 3 equals 4. Instead of saying 1 plus 3 equals 4, I would say it's 1, 3, 4. Yeah, it's a little weird, but yeah, that's what they're showing. Okay? That is NAD+. Notice our textbook, being written by some chemists, show hydride, H minus. So our textbook, I believe, sticks with the H minus. If you took a biology class, they probably are showing H plus. Okay? So H minus needs to react with that structure. So there's a lot of different places that H minus could react. Where does it react? As a hint, the answer is shown in blue. And in the blue, what have they not shown? All of this. Why not? Nothing happened to it. Okay. Why is it all there? we can't say to confuse us anymore because biology did it. So biology had a reason for it. If it was just me, yes, I'm doing it to confuse you, but it's not just me. To get into your house, what do you need? A key, right? And that key has the little ridges on it with pins. So you stick the key in and you get the pins. So the only part of the key that is important is the part that matches the pins. So when you take a look at your key, the only thing you've got is that part with the ridges on it. There's no other part to the key. Oh, the thing you hold? Yeah. Guess what's happening on here? The part that's important, that's doing the chemistry, the pin part, is our nicotinamide. The part that our molecule can now hold is the rest of that. Okay, we still need it for the functionality here, but that's not where the chemistry is happening. So the chemistry is only happening out on that end, and where out on that end is it happening? So if these electrons, because it's a source of electrons, need to come into this structure somewhere, where do they come in? That was a horrible arrow. Comes in at carbon 4. What happens if we form a bond between that hydrogen and carbon 4? We'd break the octet on carbon number 4. So what has to happen?
Electron shifts.
We have to move a pi bond. But if we move the pi bond there, what happens to carbon number 6? Break the octet. So what happens? Shift those electrons to the nitrogen. That doesn't break the octet on the nitrogen, but it does do an interesting thing. What is special about that nitrogen in its current state, in the red state? In the red state.
Oh.
It's positively charged. Does nitrogen want to be positive? No. Because of that nitrogen withdrawing electron density, that helps dump the hydrogen up at that top spot. It makes that carbon particularly more positive. Same deal for this other group up here. This group up there is helping to withdraw electrons from the structure, making that ring much more susceptible to a nucleophilic attack by a hydride. Kind of makes sense? This then sets us up with our nicotinamide in blue. The whole point is that I can shuttle that hydride off to somewhere else. So how could I reverse the process? Well, take the electrons of the nitrogen, share them back. We exceed the octet on carbon number 6, exceed the octet on carbon number 4. These electrons can go out with the hydrogen. Kind of make sense? Okay. So NAD+, super useful. Right? It's used in a lot of enzyme reactions, particularly in the Krebs cycle and particularly in the electron transport chain, because it transfers high energy electrons. Electrons in general, period, are high energy. Okay, but we're now transferring those electrons. We can use that use that energy to do other things that we'll see in the electron transport chain. Okay. Could we stack reactions? So let's take a look at what's happening in that top one, which theoretically happens over spring break, potentially, or maybe tonight after this lecture. Oh, come on, you had organic chemistry. What is the name of that compound?
Ethanol.
Ethanol. What is happening to the ethanol? Losing hydrogens, I'll accept that. Gaining oxygens, it's being oxidized. Okay? Your body is processing the ethanol, turning it into a state that allows it to be excreted easier from the body. Okay? The easiest way to excrete it is in an acid form, so this is step 1 of the oxidation process. Okay? It forms the aldehyde. Why is methanol toxic? Your body is processing methanol the same way it processes ethanol. Except in the case of methanol, we're missing a carbon. Which means in step 1, what do we form? Nobody knows that one?
Formaldehyde.
Formaldehyde. Why is methanol toxic? Step one of the process is to make formaldehyde. We don't drink formaldehyde because it's toxic. Okay? It pretty much kills all living things, which is why it's used as an embalming fluid. Okay? So methanol becomes toxic as, for one reason, it produces a very toxic byproduct in the body. Okay? And then your body can't oxidize formaldehyde very well because it doesn't have a handhold. Same idea as the key function. So it takes a lot longer to turn formaldehyde into an acid that you can then excrete. Ethanol, on the other hand, that aldehyde that we're forming, the ethanaldehyde, or the acetaldehyde, right, that compound is still toxic, but we actually want it to be toxic. That's the buzz. That is the buzz of drinking alcohol, is an aldehyde wreaking havoc on our brain. Thankfully, or mostly thankfully, that process is relatively benign-ish, as long as done in relative moderation, and we can recoup the losses of that havoc. Right? So, to do that, what had to happen? Well, we had to do an oxidation reaction, which means we lost electrons. Electrons, stupidly unstable little beings. That means they can't just float off into solution. Sorry, biology, that was crap. You can't show electrons just chilling on their own. Something has to accept those electrons. What's that something? NAD+. So the alcohol to our formaldehyde process won't happen easily until we get an electron acceptor like nicotinamide to accept those electrons. So if we have lots of NAD+ floating around, we can start this oxidation process. Right? So nicotinamide will be coupled to that reaction. Kind of make sense? Okay. What does that one look like? Even bigger, even more obnoxious, right? It's known as FAD, for flavin adenine dinucleotide, which is sweet. So we have the flavin, sorry. We have our adenine at the bottom again. And then what do we have up the top? Well, we have a sugar connected to a nitrogenous base, also known as another nucleotide. So we're looking at that dinucleotide aspect again. There are other forms of FAD. FMN is one. Flavin mononucleotide, meaning all we have is the flavin. So you get rid of the adenine. Okay? In this structure, where's our chemistry? Oh, crap. Oh, yes, never mind. I remember. Chemistry ends up happening around these nitrogens. Okay? The nitrogens were the same kind of thing that were initiating the reaction in the nicotinamide. Flavin's doing the same thing. The interesting feature of our FAD is that while it does the same thing as NAD+, it stays neutral. We go from FAD, let's see, to FADH2. Okay, so how did that happen? We have FAD to FADH2. Well, number one, what do we need? 2 hydrogens. Is it likely we're having hydrogen gas? Hydrogen gas, if you remember back in OChem, does not react well with double bonds. It reacts so poorly to get a reduction reaction with hydrogen gas. What do we need? a metal catalyst, we needed something like platinum or palladium. Okay? So H2 is not a good thing to introduce, will probably be interesting to hydrogens. Okay? Common form again would be H+. But if that was the case, what happens? What would the charge be on our product side? Positive 2. It's not positive. It's FADH2. So what does that mean had to happen? I also needed 2 electrons. Okay. So if we're looking at our half reaction, we can show those electrons. If we want to hide those electrons away, really what we're looking at, and FAD is actually better to show to the electrons. We're adding H+, and we are also adding H- to form FADH2. Okay. Why is it actually better to show it as 2 electrons? FAD can do this reaction, or the addition of those 2 hydrogens, stepwise. Okay. Stepwise by meaning it can accept 1 electron, and then it can accept a second electron. NAD plus has to accept 2 instantly. FAD can break that down into multiple steps. Because we're looking at the transfer of a single electron, we'd be making everybody's favorite reaction in OChem. A name associated with most of our political parties at this stage in the game. I said all of our political parties though, so not Republican. Radicals. We're doing a radical reaction. That's why we're going nowhere with politics, is everybody's pushed to the extremes. Or at least pretends to be pushed to the extremes. Okay. So we'd be running radical reactions. What's the issue with radicals? Is we'd end up with an intermediate of a radical. Since that radical is now just chilling around floating on its own, it's also known as a free radical. What's the issue with free radicals? They're bad, they're unstable, they destroy things. FAD is okay as a free radical because of its structure. So maybe I like that previous one. If I dump a single electron in here, do H- into this, take 1 electron out, I'll put 1 electron there. The result, if we clean that up, so I have a single bond, I have that bond to hydrogen, and then I have that single electron there. That carbon is now a free radical, and that is now potentially dangerous. But what is special about FAD that makes that free radical not so bad? Come on, electrons. Pen. And then I could potentially do something like this. And then this. And you should be saying, oh my God, by now, because what am I showing? Tons of resonance. If we have lots of resonance, what does that do to the stability? Increases it. So FAD as a radical species isn't a horrible free radical. What are horrible free radicals? You've heard the term free radical, you're typically hearing it in association with something else. Oxygen free radicals. Why are oxygen free radicals dangerous? How big is an oxygen? It's insanely tiny. There is no resonance with an oxygen free radical, okay, which then means it's unhappy, which then means it reacts very swiftly. Okay? Take it a step further. Oxygen is the second most electronegative element. Its oxidation state should be -2. If it's a free radical, is it -2? Nope. It's insanely pissed. Wants that electron. It will steal it from the closest available source, even if that closest available source happens to be what's keeping that organism alive. Okay? That's why free radicals are bad. Okay? Are they important? Absolutely. We have to transfer electrons, but we have to transfer those electrons in a controlled fashion. Using free radical oxygen is not a good idea because that's not very controlled. Flavin, or I'm just going to say FAD. FAD will be a lot better of a transfer because it can do resonance to temporarily stabilize that radical for long enough that it doesn't destroy stuff. Kind of neat. Okay. After that, we've got ATP. How many electrons are transferred in ATP? Trick question. Why is it a trick question? You don't transfer electrons.
Phosphate group.
You're transferring a phosphate group. Okay. So there's not a transfer of electrons when we're using ATP. It's the transfer of a high energy phosphate group. Okay. What we'll talk about on Tuesday would be why that is a high energy group. So why is there so much energy released within this process? So consider that it is a question on the homework. So if you're working through the homework, you might be like, oh, those are some interesting things on what might cause this to be a high energy reaction. Okay. And with that, for the first